see that, Don.
Folks, yesterday I left you with a reminder. The reminder had an error in it. The video that I wanted you to look at had been numbered 00039, not 00036. 00036 was a lecture from past 2046 class of mine on electrochemistry. Perhaps you did recognize the correct video to look at based on the title, Periodic Size Trend Analysis. But to make the video that I want you to look at mesh directly with lectures from our gathering this term, I've renumbered it. It's now 5041 and fits right in with where we are at this point.
So I've been working through past exams. I've noticed that there's not much on like periodic trends and like what we're going over now. What exactly are we going to be tested on Friday?
What do you think?
I'm asking, so that
What do you think?
probably similar to what the exams are.
Probably somewhat.
Most likely similar to what the.
Not similar. I want material. Tell me what you expect to see on this exam regarding ChemNotes content.
21, 22.
How about that?
Okay, I'm just double checking.
I'll remind you.
All right, thank you very much.
Okay. I may have a question or two on this Friday's exam about this size trend stuff. Okay?
That's not so.
But the stuff we're really wanting to get at, Chapter 23, again, establishing a basis for rationalization of strengths of bronzosyloric acids and bases. That I'll hold till the last exam.
Thank you.
So, again, be sure to look at this if you've not done so. My apologies for giving you an incorrect reference yesterday. I'm afraid I'm not very good at this computer-based stuff. I'm just learning it. I wasn't born with computers like you folks. I was born with slide rules. Most of you probably have never even seen a slide rule. I don't know. So I admit that when I monkey with computers, if something goes wrong, I'm usually at a loss regarding how to fix it. In any case, to my knowledge, all lectures through yesterday are now available in numerical sequence. And I am not seeing any videos that you are barred from watching because of the video being labeled, what, private content or something like that. As far as I know, that's all been cleared. But if you go to see a video of concern and you are barred from it, send me an email so I can get this thing fixed. Okay? I don't think you'll find any, but I know we had this problem when Mr. Mosen was here. And I caught it when I was in Vietnam, because I went to look at the videos in the hotel lobby in Saigon. And I couldn't get in, because it said this private content or whatever, for private viewing only or some damn thing. So I immediately contacted Mosen, and to my knowledge, that problem was fixed. What somebody reported to me yesterday, I don't know, maybe it was you, about still running into this. As far as I know, it's cleared up. But if you go to a video and you get blocked, tell me. Okay. Now, to review, I want you to look at this so you'll understand the rationale that underlies explanation of atomic size trends, which applies to A family atom, not B family atoms. When atoms, like the transition metal atoms, have valence electrons other than S and P. Size trends get strange. There's no pattern to it anymore. D valence electrons, there's no rationale that, pardon me, that I know of that can be applied. And on occasion, you'll find atoms of elements like the lanthanides and the actinides, which appear to have F valence electrons. Again, there's no pattern in the size trends for these things. So A family atoms only, which is not a consequence for us because this rationalization of Bronsted-Lowry acids and bases will consider species which include only A family atom composition. Again, left to right across a period, as you go from atom to atom, you generally see a small shrink in size. But I know of no exceptions of a right side atom being larger than a left side atom for A family atoms as you go left to right. Okay? Why? In the main, because Z effective is increasing left to right. Remember what Z effective is? Z effective is the actual nuclear attraction which valence electrons feel by the nucleus of the atom for the configuration the electrons are part of. Okay. And that's grossly different, Z effective, from Z itself. What's Z itself? Just to be sure you understand the language. What's this? Atomic number. Hey. If nothing else, lithium, sodium. Lithium 3 protons in the nucleus, sodium 11. More than 3 times as many. Yet sodium is larger and easier to ionize. Considerably larger and considerably easier to ionize. So Z effective for the valence electron of lithium has got to be greater than Z effective for the valence electron of sodium, which clearly distinguishes Z effective from Z itself. Top to bottom, as we go down the family, for A family atoms, we see a big size increase as you go from period to period. For the atoms which share the property of being in the same period. Sodium a lot larger than lithium, potassium a lot larger than sodium, chlorine a lot larger than fluorine, bromine a lot larger than chlorine. Well, that means Z effective is decreasing substantially as atom size increases. From a theoretical standpoint, as a reference, you can take a look at radial probability graph A. Take a look at that right now, if you will. That's on page 2310. Radial probability graph A compares the radial probability functions for 1s, 2s, 3s, and 4s electrons and shows you that MPD, the most probable distance of a 4s electron from a nucleus, is considerably greater than the most probable distance of a 3s electron from its nucleus, 2s electron, 1s electron. So that means, if we're talking about an atom of potassium, which has in its configuration 1s, 2s, 3s, and 4s electrons, with the 4s electron being the outermost valence electron. If I am at the center of a potassium atom, and I'm looking to the exterior surface of the potassium atom, at or near the exterior surface, I'll see the 4s electron, because that defines the size of the potassium atom, because its MPD is greatest. For all the electrons which are part and parcel of the configuration of potassium, the 4s electron is considerably further from the nucleus. So it determines the size of the potassium atom. But I'll also see 3s pair, 2s pair, and 1s pair. all getting considerably closer to the nucleus as I go from the 4s outermost electron to 3s to 2s to 1s. Distance from the nucleus. How will, it's all right, for potassium versus sodium. Potassium versus sodium. If in one instance I'm standing at the nucleus of a potassium atom, the second instance I'm standing at the nucleus of the sodium atom, and I choose to look at the 3s electrons. I can't look at 4s for sodium, and I haven't gotten any. Which of these 3s electrons will be closer to the nucleus? Those of potassium or those of sodium? Potassium. Hey, same kind of electrons. But whatever Z effective is, it's got to be in some way proportional to 19 protons in the nucleus. So the 3s electrons of potassium are closer to the nucleus of potassium than is the valence 3s electron of sodium. How about the 2s electrons? Still closer for potassium. How about the 1s electrons? Much closer for potassium. Because the 1s electrons, for any atom, are practically speaking not shielded from nuclear charge at all, except for the small degree of shielding that the 1s pair exert on each other. If you listen to this video, watch this video, you'll hear my explanation of how and why we can recognize that electrons in the same orbital do shield each other somewhat. Not substantially, but somewhat. Slightly. It has to do with comparing properties of hydrogen versus helium, no more, no less. Hydrogen 1s electron, helium 2s electrons. 2 1s electrons, pardon me. Well done. Helium 2 protons in the nucleus, hydrogen 1 proton in the nucleus. And Coulomb's law, written as a proportionality in terms of force, is this. You've seen this before. What do the Q terms represent? Charge. For an atom, what charges are we talking about? If I'm considering, for example, application of Coulomb's law to hydrogen or helium, what do these Q terms correspond to? Well, for hydrogen, it's easy. It has to be the charge on the single electron which it has and the proton in the nucleus. For helium, Q again represents the charge on a single electron. And the other Q represents 2 protons, the total nuclear attraction. What's D? The distance between the electron and the protons in the nucleus. Well, this shows you the force falls off as the size squared, which accounts for Y. As atoms get progressively larger, hey, their ionization energies are falling off substantially. Okay. Now, the argument that I present, the argument you'll hear in this lecture, has to do with comparison of ionization energies. Now, for hydrogen, it only has one ionization energy because it's only got one electron. Okay? So the comparison that I wish to make to decide that 2 electrons in the same orbital shield each other at least a little bit is comparing the ionization energy of hydrogen to the first ionization energy of helium. Now, what's this thing tell us? Given that helium size-wise compares how to hydrogen? Helium, hydrogen. Which one's larger?
You mean hydrogen?
Well, I had 2 votes. Hydrogen is larger. Keeps with the size trend, left to right. Measurements verify that the hydrogen atom is bigger than the helium atom. Okay? Well then, how must the first ionization energy of helium compare to the first ionization energy of hydrogen? How must these ionization energies compare? If the two 1s electrons for helium do not shield each other at all from nuclear charge. Because when we're looking at hydrogen, this is 1 times 1 over the hydrogen radius squared. When we're looking at helium, this is 1 times 2, or 2 times 1, who cares how you write it, okay? Divided by the helium radius squared. How must the first ionization energy of helium compare to the ionization energy of hydrogen? If the two 1s electrons of helium do not shield each other at all. You heard the word shield in 2045 lecture? What shield mean?
It's repulsion.
More specific.
It's like an effect, kind of. It's like the electrons kind of, I don't know what it actually.
It makes it easier to extract, like, to remove.
What is that?
It makes it easier to remove an electron.
Does it have to do with the spin? Like the upspin, downspin?
I ask this question because these words are used, and if you don't know what the words mean, then you don't know what the conversation's about. All right? Pictures. Here's H. Here's helium. Now let's go to lithium. First, it's a lot larger, but there are 3 protons in the nucleus. And these two sizes are defined strictly by 1s electrons. That's all these things got. Okay? But the size of this thing is defined by what? What? 2s electron. That's the outermost valence electron for lithium. Where will I find the 1s electrons of lithium relative to its nucleus compared to these 1s electrons for hydrogen and helium respectively?
Closer?
They're going to be closer. So let's put these two 1s electrons, the 1s pair for lithium, in our picture, closer to the nucleus. Okay? But out here is this 2s electron. The electron which defines the size of our lithium atom, because it's the outermost electron. Nothing fancy about that. Now back to shielding. Can there be any shielding for the hydrogen atom? Yes or no? No. Because shielding is a term which applies to the various electrons in an electron configuration for an atom, which interfere with the ability of a particular electron, like a valence electron, from feeling nuclear attraction. That's what shielding is about. So when we get to lithium, we're really looking at the first atom in the periodic system where shielding is consequential. Why is this true? How is shielding consequential for lithium?
The 2s electron is going to be ionized as opposed to,
I want you to talk about electrons.
I mean, there's spinnings they're creating.
I don't care about spinning.
As far as shielding is concerned, the 1s electrons are going to prevent the 2s electron from getting closer
Yeah.
to the nucleus.
Right? Because these things are close to the nucleus. This thing is much farther away. So these two have what effect on the ability of this outermost valence electron to feel nuclear attraction? Do these increase the ability of this to feel nuclear attraction, or these diminish the ability of this to feel nuclear attraction? Well, let's look at the properties of lithium. Number one, it's a hell of a lot bigger, even though it's got more protons in the nucleus, right? 3 times as many protons as this to hydrogen. 1.5 times as many as helium, okay? But this is a good deal larger than either of these. And what do we find about the ionization energy of this? First, ionization energy. The energy associated with removing this 2s electron. It's much smaller than either of the ionization energies for these. Well, that's telling us. Independent of the fact you got 3 protons here, these 2 electrons are shielding this electron effectively. They make it easier for this electron to be lost by ionization process. They interfere with the ability, they prevent this electron from feeling nuclear attraction. That's what shielding is about. Okay? So let's go back to what I was saying. By comparing the first ionization energy of helium to the ionization energy of hydrogen, how can we conclude that electrons in the same orbital do shield each other somewhat? Back to hydrogen and helium. This atom, hydrogen, is bigger than this atom, helium. All right? And here's Coulomb's law, in this case applied to helium. And this term for helium is smaller than this term for hydrogen. Okay so far? Well then, how must the first ionization energy of helium compare to the ionization energy of hydrogen if these 2 1s electrons of helium don't interfere with each other's ability at all to feel nuclear attraction?
It's going to be very much.
How much greater?
Twice.
Depending on the size of the distance to atomic radius.
I want to know if this first ionization energy of helium would have to be more than twice as great.
Yes.
Would have to be more than twice as great, wouldn't it? Because this is 2 times 1 for helium, it's 1 times 1 for hydrogen, and this is a smaller value for helium. You agree with that? We're just looking at the arithmetic that's shown to us by this expression, Coulomb's law written as a proportionality. This thing is telling us, applied to hydrogen versus helium, that if these electrons don't interfere with each other's ability at all to feel nuclear attraction, the first ionization energy of helium has got to be more than twice the first ionization energy of hydrogen. More than twice. Because you got 2 times 1 versus 1 times 1, and D is smaller. Okay? That's just simple arithmetic, no more, no less. So now let's look at the observed properties. Because that's how we find out if these theories are correct. We go to the laboratory and make measurements. Because when we go to the laboratory and make measurements and get facts, if the story we've cooked up doesn't fit the facts, we better throw away the damn story and cook up a better one. If you are in a science class where the lecturer gives you the impression that a long time ago some smart chemist or physicist sat down and figured out the explanation, and then all the atoms, for example, in the chemistry class, all the atoms now behave in accord with the theory? Baloney. You're dealing with a bold-faced liar. Atoms don't give a damn what we think. They never have and they never will. They don't care what we think, they don't care what we say, they don't care what we calculate. They behave as they behave, and it's our job to do the best job we can to explain this behavior. So if we come up with an explanation that doesn't fit the behavior, we better fix the explanation, because that's what's sour. Now, we can affect how atoms behave. Blow up bombs, that changes the way they behave. Hit them with energy, that changes the way they behave. Heat them up, that changes the way they behave. But talking and thinking and creating ideas doesn't change anything. So now let's look at these first ionization energies. And what we observe is that the first ionization energy of helium is not quite twice as great as the first ionization energy of this. I got the numbers here someplace. Let's see what I got. Helium 2372. That's kilojoules per mole. And hydrogen is 1311. Well, if I double this, I got about 2600. Okay? And we said, these two electrons don't interfere with each other's ability to feel nuclear attraction, the first ionization energy of this has got to be more than twice that for hydrogen. Well, here's the ionization energy for hydrogen. And if I'll double this, I get a number that's somewhat bigger than 2600. This is not quite that big. So this is telling me what I needed to know. That is to say, do electrons in the same orbital have any shielding effect on each other? The answer is yes. Not much, but still yes. I mean, after all, when we put lithium into this game, IE number 1, we get 520. Ha-ha! 3 protons in the nucleus. Yet look at this ionization energy. That's pretty small compared to the ionization energy for hydrogen, and damn small compared to the first ionization energy for helium. This is how we know whether or not these stories are true. By looking at observable properties. It's amazing, these ringtones that these machines have. I get Beethoven's Ninth Symphony. That's good stuff.
Mom and Dad.
Okay, enough on that. Now again, you'll hear this story told, I think, more elegantly if you look at this, which is why I want you to look at it. Now, as you proceed through chapter 23, you'll see a table of electron configurations. 23.4, 23.5, 23.6. I put that table in purposely because the most important periodic property by far, which I believe we've already mentioned, for an atom is what? Structure. What structure?
I'm sorry.
No, I didn't say you're wrong. What structure are you talking about? Huh?
Of the atom?
An atom. What structure does an atom have?
The electronic, the
Go on.
configuration.
Electron configuration. That's the structure we're concerned with. And the most important periodic property is a specific part of this electron configuration for each atom. What part are we talking about? The what? Yeah, the valence configuration. You betcha. The valence configuration for an atom tells us more about how this atom will behave than any other single property. Size, ionization energies, chemical, physical behavior, all this stuff is relating to that valence config. Now, you did this in 2045, but I don't know how sharply and clearly they made a point of this. I don't know what to say. I mean, when you start playing this game of recognizing that atoms most commonly tend to react so that on reaction they develop a configuration which is parallel to that of nearest neighbor noble gas, well, then it stands to reason that these noble gases must be damn stable electronically. Because that's the way these atoms are behaving when they react. They want to get a configuration that's as stable as possible. So they react to get configurations which are like nearest neighbor noble gases, because these noble gases are the stable ones, right? And that depends on valence configuration. It accounts for why, for example, metal atoms on reaction with nonmetal atoms. The metal atoms wind up being the electron losers to gain noble gas configuration, and the nonmetal atoms become electron gainers. Really, it's nothing more here than counting and talking about energy expense. If sodium reacts with chlorine, and I look at the valence configs, sodium's got 1 valence electron, chlorine's got 7. My golly. It doesn't take much fancy thinking to realize for sodium to get an electron configuration that's noble gas by gaining electrons. How many electrons would a sodium atom have to gain? Because its nearest neighbor noble gas by gaining electrons is argon. You count the number of electrons sodium would have to pick up to become like argon. 7 of them. Well, what do you think's cheaper? Lose 1 or gain 7? Because after you turn an atom into an anion, it now starts to cost a hell of a lot more energy to put more electrons in there. Because a negative thing repels incoming other negative things. Not in school. I erased it. So I tell my class, there's no more fundamentally important law in the world of chemistry than Coulomb's law. Because you have to understand how electrons behave, and their behavior is dictated very much by the protons in the nucleus. So you can't get away from this plus or minus stuff. But when you look at chlorine, it's got 7 valence electrons. So you think chlorine can readily lose 7 valence electrons and become a chlorine 7 plus cation, and then it's noble gas? There's no such a species known. A 7 plus monatomic cation. But on the other hand, if chlorine picks up 1 electron, then it's noble gas. So what do you think is cheaper? Picking up 1 or losing 7? Well, you could do the energy analysis to find out. Picking up 1 is a hell of a lot cheaper. And in fact, chlorine, like most atoms in the periodic system, have an electron affinity. You remember what electron affinity is? I symbolize it E minus A, electron affinity. This is the change in energy associated with an atom collecting an electron. No more, no less. There's the equation which corresponds to electron affinity 1 for the chlorine atom. I'll bet you talked about electron affinities in 2045. Did you learn that most atoms in the periodic system have a first electron affinity which is exo? Did you learn that? That means most atoms in an environment where they can collect an electron will in fact collect the electron. Hey, you know why, you know how to explain this for chlorine. Hey, now it's noble gas. Its electron configuration got quite stable. This is exo. In fact, the first electron affinity for chlorine is the most exo electron affinity. More so even than fluorine. Has to do with size. Fluorine's first electron affinity is quite exo, but not as exo as chlorine. The argument goes that when you take fluorine, turn in fluoride ion, the compactness of the electron cloud brings in a little bit more electron-electron repulsion than what you have when you add an electron to this thing, because it's a lot bigger atom. Hey, interesting, isn't it? Did you also learn that an energy change like this has a delta G value which is the same as delta H? Did you learn that? Notice there's no minus T delta S over here. Why not? Why for this process? For this process, since delta G is equal to delta H, then it must be true, never mind the temperature, that delta S has what value?
0.
Yeah, okay, good. Why? Why is delta S 0 for this thing? Because what I'm really saying is the entropy of this and the entropy of this must compare how? They're the same. What kind of entropy do you think this thing has? 0. In order for a piece of material to have an entropy, it's got to have a mass. You know what kind of mass this has compared to the mass of a chlorine atom? Nothing, practically speaking. Absolutely nothing. Delta S for this is nothing. which is why this is true. It's just stuff which I think helps you better understand this kind of stuff. In any case, back to these questions. We're now looking at the questions on page 23.7. And I don't know why I had question 23.1 here. It's not a bad question at all. Question 23.1 is just reminding you that ionic compounds are brittle because the ionic crystal lattice is characterized by a regular, organized, repeating array of positive ions surrounded by negative ions, which in turn are surrounded by positive ions, etc., etc. Well, if I take this ion lattice, like a sodium chloride crystal, and I try to reshape it by bending, what do? I start forcing plus ions to be next to plus ions and minus ions to be next to minus ions. That creates repulsion, and boom, the crystal explodes. That's why the ionic compounds are brittle. But never mind that. I don't know why I put that there. Let's go to 23.2. Copper and chromium. This is 24 and 29. The question is, what are their ground state configurations, for starters? I ask because when you learned about atomic electron configurations in 2045, did you not recognize that chromium was the first atom which develops an electron configuration that's not predicted by the Aufbau order? Atoms, hydrogen on down through number 23 vanadium. Every one of those configurations can be written by the Aufbau order. You learned about the Aufbau order. 1s2, 2s2, 2p6 and all that stuff. But when you get to chromium, Chromium is argon core, which represents 18 electrons in one fell swoop, followed by, well, this is 18, so we got to have 6 more. All right? Now, if we were going to develop the chromium configuration based on following Aufbau, after argon, what electrons go in next? 4s or 3d? After argon. Well, what's configuration for potassium? Is it 4s1 or 3d1? 4s1. Calcium. Has it got any d electrons? No. So when we get to scandium, we're looking at the first atom in the periodic system which has a d electron in its configuration. But we have recognized that the 4s sublevel fills before 3d gets any electrons at all. Okay? For most atoms. So we'll write 4s2, 3d4, and then we'll put quotes on this. Because this is the configuration predicted by Aufbau, but it ain't right. What is right for chromium? It's argon 4s1, 3d5. Now then, if I subject chromium to its first ionization energy, I got my ionization cannon loaded up with energy. Bam! I just pumped enough energy into this to knock away an electron. The electron which I knock away will be that which is of lowest ionization energy, the one which is most loosely held, the one which feels the least Z effective. Which electron do I take away? I take away the outermost. Well, is it one of these or is it this one?
4s.
I take away 4s. So I've now recognized something else because there's no exceptions to this whatsoever. When I subject atoms to energy the purpose of which is to ionize the atom by losing electrons. The highest N value electrons always go first. Well, that tells me something. It tells me that as soon as I put this single as soon as I put any d electrons in a configuration, how does the energy of the 3d sublevel now compare to the 4s sublevel? Let's go to scandium. 21 scandium. Scandium I'm picking on because, again, it's the first atom in the system which has got a 3d valence electron, or the 3d electron in its configuration. Here's the way I made the configuration. I added electrons to 4s sublevel before I put in this electron, because that is the way I developed the configurations for potassium and calcium, the two atoms which immediately precede scandium in the periodic system. Okay so far? Now I'm going to ionize this guy. Well, this was the last electron added. So if the ionization process anti-parallels the electron configuration development process, when I ionize this, I'd expect to remove this. But I don't. When I ionize this, I make scandium single plus, which has the configuration 4s1 3d1. And when I make scandium double plus, I make a species with the configuration argon 4s0 3d1. And I don't touch this until I put the third ionization energy in there. Well, that tells me something. Maybe I developed the configuration in accord with Aufbau by filling 4s before 3d. But now I know, as soon as I put any electrons in 3d, the 3d sublevel is more stable. So the hell with writing the configuration like this. I'm going to write it this way. Because as soon as I put electrons in 3d, the 3d sublevel is more stable. So I want this written as an energy relationship, with the electron which is least stable, the loosest electron, the one that's most easily removed, at the end of this string of electrons. So when I write scandium, I'm not going to write this. I'm going to write this. For the same reason. As soon as I put this one electron in 3d, this thing is now more stable than 4s. Right. So let's write it like this, independent of the order in which we put the electrons in to make the configuration. Okay? So now we go back to chromium. On what basis did you learn in 2045? Now I'm fishing again, 2045. On what basis did you learn to rationalize this configuration for 3D5 4S1, as opposed to 3D4 4S2? Did you hear about a gimmick which can be used to rationalize this configuration? Did you hear anything about this? Or were you told, memorize it and that's it? I don't know what you heard. Tell me what you heard. Surely you looked at this configuration. Did you hear anything about this? Hand waving? Blinking? What did you hear?
This is just in the back of my memory. Does it have to do with molecular orbital theory?
Nope. How can you apply molecular orbital theory to an atom?
I mean, they're like...
There's no molecules here.
Okay. And that has to do with bonding?
There's no bonding here.
Okay.
T has 5 orbital pairs, all.
Well, let's make a line diagram for a 3D sublevel. You did this before.
Spins are filled all down.
There's a pictorial representation of the 3D configuration for chromium. All right? Well, before we proceed, let's look at copper. Copper based on Aufbau. Copper based on Aufbau would be argon 4s2 3d9 or 3d9 4s2. But copper is not that. It's not showing a configuration predictable by Aufbau. Instead, copper is argon 3d10 4s1. So if I make this line diagram representation for the D sublevel configuration for copper, then every one of these orbitals is filled up. So when I looked at this and I'm trying to tell my students something about this, I said, all I can say is, for reasons that I don't understand, and I don't understand. Now, I don't know if anybody really understands it. A half-filled or completely filled large capacity sublevel. Do you agree that a 3D sublevel is a large capacity sublevel because you can put as many as 10 electrons in it? A half-filled or completely filled large capacity sublevel like 3D is particularly stable for reasons we don't know about. Half-filled or completely filled. Half-filled, 5 electrons. Completely filled, 10 electrons. So I asked my theoretical buddies about this. Because on occasion the theoretical guys come over here and teach general chemistry. And they told me the answer lies in quantum mechanical exchange energy. So I said, what the hell is quantum mechanical exchange energy? So they start talking to me about differential equations, and I said, forget it. Not because I reject their explanation, but because I do not understand it. And I contend that if the only way you can explain something is by writing equations, you don't understand it either. But it fits the facts. So, that's how we rationalize this. Now, 23.3. This has to do with writing configurations for atoms by analogy. All right? 23.3 says this question. If I'm going to consider electron configurations for molybdenum, silver, tungsten, gold, what might I expect? Well, I'm going to look at my periodic table and I see that silver and gold are in the same family as copper. And I see that molybdenum and tungsten are in the same family as chromium. And what I recognize for chromium and copper, they have configurations which are not predictable by Aufbau. They have this half-filled or completely filled large capacity sublevel application, whatever. So I'll say, okay, I will, by analogy to copper, say silver is 4d10 5s1 rather than Aufbau predicted, which would be 4d9 5s2. And then I'll go to the lab and I'll make some measurements to find out. Well, I'm correct. So I'll go back to molybdenum. I said, chromium is an exception. 3d5 4s1, so I'm going to bet molybdenum is 45 5s1 and not 44 5s2. And I make some measurements on molybdenum. Right again. How about that? So I go back to gold. Same family as copper. So I'm going to bet for gold 5d10 6s1. And I'm right again. Now let's go to tungsten. Or if you prefer, I'll call it wolfram. That's where the W comes from. That's the old Latin name for tungsten. Wolfram. That's where its chemical symbol comes from. And I predict for wolfram, tungsten, a D5S1 config. And now I'm wrong. Tungsten goes back to Aufbau predictable configuration. Question, why? Answer, you can't find anybody that knows. I asked my theoretical folks, they don't know. You want to see some more screwiness? How about the nickel family? Nickel's configuration is predictable by Aufbau. Well, if I tell you the nickel configuration is predictable by Aufbau, you know its valence configuration is 3d8 4s2. Okay so far? That's nickel. D8s2. Well, how about palladium and platinum? They're in the same family as nickel. What would you predict for palladium and platinum? Nickel. Predictable by Aufbau. Nickel is argon, 3d8, 4s2. So for palladium platinum, would you expect D8s2? Immediately paralleling this configuration for nickel and following from Aufbau? Not unreasonable, is it? It's quite reasonable. Then you look at palladium and platinum, and neither one is D8s2. Then you look further and you find out not only are palladium and platinum not D8s2, palladium and platinum don't have the same configurations as each other. What the hell's going on here? Because the only thing I know for sure about palladium and platinum is that, like nickel, they got how many total valence electrons? 10! Aha! It's this abundance of valence electrons which makes this transition metal chemistry very interesting and often very difficult to understand. That's why I postponed discussion of transition metal chemistry till the last chapter, really, in what we do in this course, chapter 24. Interesting chemistry, but screwy in many cases, like this. So, I start looking for information on palladium and platinum. And I find out one of these atoms is diamagnetic in the ground state, and the other one is paramagnetic. Yet neither has the same configuration as nickel, which is also paramagnetic. Well, that tells me, if the configurations of palladium and platinum must also have 10 valence electrons total, and one is diamagnetic, and one is paramagnetic, but the paramagnetic one is not the same as nickel, then the only remaining configurations are D9, S1, and D10, S0. That's it. It can't be anything else. Look at the table of configurations. Remember, it's in the notes. See who's what. You see palladium and platinum in there? Which one is which?
Palladium's the D10.
Palladium's D10 and platinum's D9S1. Interesting. I mean, a few years back, there was a person applying for a general chemistry lectureship position. And they were asked to talk about this fundamentals of electron configurations for transition metal atoms. And the first thing out of this person's mouth is that when we get to the transition metals, we can successfully predict configurations by analogy. I said, what? And this person went so far as to talking about the nickel family. And said, since nickel is D8S2, that guarantees that palladium and platinum are D8S2. You're out. You lose. Because these atoms don't give a damn what we say. They are what they are. And when you make a statement so flatly wrong as that, at the minimum you've told me you haven't prepared for this presentation at all.
Are all these orbitals just interfering with one another?
How do you mean interfering with one another?
Like wave, like three-dimensional wave interference?
No. These various sublevels and orbitals thereof are said to be orthogonal. You ever hear that fancy word?
Yes.
Orthogonal? What does orthogonal mean?
180, or at right angles?
It means, practically speaking, that they don't interfere with each other.
Okay.
Because when you look at these radial probability graphs, for example, okay, and you overlap, here's 2p. Well, that's not a very good picture. 2p, okay, and then here's 2s. All right?
Right.
This picture is suggesting that 2s electrons and 2p electrons change their nature from time to time. Sometimes this electron is 2s, sometimes it migrates to the other orbitals to p. No. 2s electrons are forever 2s electrons, and 2p electrons are forever 2p electrons when they're in the same configuration. I mean, when they're in a configuration for an atom. That means these orbitals are not interfering with each other. They're orthogonal. Interesting words. I don't even bother with that in my class. In any case, now then, last question, 23.4. Ground state configurations for copper and chromium, which we've just looked at. This is chromium. Remember, Aufbau predicted for chromium 3d4, 4s2, which we wrote quotes on because that's not correct. How by measurements which you learned about in 2045, I hope, measurements which you learned about in 2045, measurements made on electron configurations for atoms. How could I go to the laboratory, assuming I had the wherewithal to make these measurements, and prove that chromium ground state was this, not this? What measurements would I make? If I had the ability to make the measurement, what measurement would I make? What property of this configuration would you measure? What is it? What is it?
pH.
pH.
One dissolve. pH one dissolve.
pH? You tell me how a measurement of pH for chromium dissolved in water, which it won't do, would possibly help you resolve this.
I mean, the
No.
looking towards Lewis. I mean, I guess like the definition of Lewis acids would be how readily they would donate electrons. No.
No. Talking about a measurement you heard about. A measurement related to valence electron configurations. I heard it. What is it? Paramagnetic character, absolutely. Measure paramag character. Tell me, what is paramagnetic character based on?
Whether or not you have electrons paired with one another.
Well, it's really based on the number of half-filled orbitals you have. Fair enough? Because a half-filled orbital means one electron. That's it. Okay? Because the Pauli principle told you that when I got a bunch of half-filled orbitals in the configuration, all the electrons, all the single electrons in each of the half-filled orbitals, they're all spinning in the same direction. So the more half-filled orbitals I have, the greater the paramagnetic character, because the electron spin, since they're all in the same direction, don't cancel each other. They support each other. So, Aufbau predicted for chromium, how many half-filled orbitals? 4. How many half-filled orbitals truly? 6. So I use a recipe which tells me total paramagnetic character based on number of unpaired electrons, number of half-filled orbitals, and I find out chromium shows a paramagnetic character proportional to 6 half-filled orbitals. So that's how I can resolve the fact that chromium is truly this and not this. Now let's go to copper. I know that copper is truly this. But Aufbau says this. Can I resolve this with simple paramagnetic character measurement? Yes or no? Why not?
They both have one.
They both have one half-filled orbital. What's the difference? This has got a half-filled S. Some level. I mean, orbital, and this has got a half-filled D. So this was not quite so straightforward. However, refined measurements on paramagnetic character, in fact, allow us to determine if an electron is F, D, P, or S. Because the paramagnetic character of an S electron is not quite the same as that of a D electron. Right. You wouldn't know that now. But at the minimum, by just counting up the number of half-filled orbitals, you can't distinguish between these two configurations. That's all this was about. No more, no less. Now then, atomic properties. Let's close today with a few remarks about this fact. How do you like that statement? Atomic size is a real can of worms. What's that mean? That means trying to determine atomic size on an absolute basis is, forget it. I mean, we've already recognized these electrons are determining the size of an atom, and they're never at the same place at the same time. They're all over the place. So you get pretty much average value information for size. But now, we are going to concern ourselves with establishing a basis for rationalization of bronze-telluric acids and bases. So we're going to be talking about not free atoms, but bound atoms. All right? So let's take a look at this. My $64 Van Gogh sketch of a nitrogen atom. All right? There's two nitrogen atoms, except these two nitrogen atoms are covalently connected to each other. If a nitrogen molecule is observable, given that 79% of this atmosphere in here called air, 78% is nitrogen. So we're going to adorn you with the very best glasses that you can have, and you say, ha, I see a nitrogen molecule. What's it look like? Shape-wise, what's it look like? I want to know what this nitrogen molecule looks like. Tell me its shape. You're seeing this floating around in space. What does it look like? Does it look like a horseshoe? Dempster dumpster? Mack truck? A bone? Rubber band? What's this thing look like? You got glasses on now, you can see it. And you do this stuff in 2045? I don't know what the hell you do in 2045. What does a nitrogen molecule look like? I've now given you the ability to see them. And this room is full of them. What does it look like?
Two spheres or
Two spheres. Does it look like this? Does it look like this?
Overlapping spheres.
Overlapping spheres. So what does it look like? Does it look like a dumbbell? When the nitrogen atom bonds with the other nitrogen atom to make the nitrogen molecule, from a theoretical standpoint, valence orbitals in which the bonding electrons reside overlap with each other, don't they? And they wind up giving a shape for the nitrogen molecule which looks like an egg. It looks like an egg. Hey, if you take two spheres and push them together, without this kind of distortion. That's what you're going to get. A nitrogen molecule, in fact, looks like an egg. Here's where the valence orbitals merged with each other, overlapped. And here's the region in space where the bonding electrons reside. So let's get to the question. Free nitrogen atom, two nitrogen atoms, except they're covalently connected to each other. How does the size of a nitrogen atom in the nitrogen molecule compare to the size of my free nitrogen atom? They're the same size? These atoms bigger? Because I could get at the size of a nitrogen atom in the bound state, in the nitrogen molecule, by observing this bond length and dividing it in two. That'll give me a measure of the covalent radius of nitrogen with the nitrogen in the nitrogen molecule. Which one is bigger? The bound nitrogen atom or the free nitrogen atom? Which atom is bigger? Free. On what basis would you argue that?
If you look at the covalent radius versus the atomic radius,
Why is the covalent radius shorter?
because it's half of the distance between the two covalently bonded atoms.
Well, I agree with that, but why does that guarantee that it's shorter than the atomic radius? I mean, you want me to draw the molecule like this? Don't be misled by the picture I put on the board.
The triple one brings it really close in, and since there's a bunch of protons,
On what basis do you argue this?
the triple bond thing,
Yeah.
it's the strongest, or it's a really
Oh, I agree with the triple bond is the correct representation of the bonding electrons for the nitrogen molecule. What I'm asking is, why should these electrons be closer to the nucleus than they are for the free atom?
because there's double the protons there.
Well, I've got double electrons too.
Well, protons outweigh electrons in terms of charge.
In terms of charge.
That chart does it.
Charge on electron, charge proton, exactly the same. Different in sign, but exactly the same magnitude.
Is it due to orbital length?
Tell me, this is a practical issue that we're getting at. As you look around the world in which you reside, do you believe that it's fair to say that most atoms with which you are familiar are bound atoms rather than free atoms?
Yeah.
Carbon atoms, hydrogen atoms, oxygen atoms bound to each other. You think the iron atoms in a piece of iron are strongly bound to each other? If you don't, go home, take up your hammer, and go whack yourself in the head with it. See if the hammerhead falls apart. It won't. Those iron atoms are really bound strongly to each other. Tell me, do you believe that in order for bonds to form, because clearly we live in a state of matter where atoms are more commonly bound to each other than they're not bound to each other, do you believe that it must be true that electrons are getting more stable when atoms bond with each other? Valence electrons get more stable? Well, how can they get more stable if they get further from the nucleus? They got to get closer to the nucleus, right? Because the only part of an atom which stabilizes the electrons which it has are the protons in the nucleus. So it follows as night on the day. When atoms make bonds, the atoms must get smaller because the electrons are getting more stable, and the only way they can get more stable is to get closer to the nucleus. How about that? We'll pick it up from this point tomorrow.